this lesson, we'll continue looking at mass-to-mass stoichiometry, but we're going to take that mass-to-mass stoichiometry to find a limiting reactant in a chemical reaction. So this was the homework problem that was assigned for you guys to do for today. And it says we have 3.25 grams of sulfuric acid in water, and that's reacted with more than enough sodium hydroxide in water. How many grams of water will be produced? So the water that's being produced is not the same water that the sodium hydroxide or the sulfuric acid are dissolved in. All right, so we got to figure out the formulas for sulfuric acid and sodium hydroxide. Anytime you have an acid name that has an IC ending but has no hydro prefix, that means you have a polyatomic oxyanion in the formula. And the polyatomic oxyanion has an ATE ending. So if you look on your in your test references at the common ions, or the common ions list, we're looking for a polyatomic oxyanion with an IC ending that sounds something like this, sulfuric, and that would be sulfate here. Okay? So we've got an acid formula then that has a sulfate ion. And if we're going to have an acid, then we've got to have hydrogen ions. Those have a 1+ charge. So to balance this out, we need 2 hydrogen ions. And the formula then for sulfuric acid is H2, H subscript 2, SO4. Okay? And then sodium hydroxide. Sodium has a 1+ charge. You find that in the first column of the periodic table. And all of the metals in this column are 1+, and hydrogen most of the time is going to be 1+. And we're putting it with its hydroxide. Hydroxide is a polyatomic ion. It's just one that you have to know. It's kind of unusual in that it has that IDE ending, but it's still a polyatomic ion. But when you see hydroxide or hear that word hydroxide, you have to know that it's OH negative. Let's see, OH. To go by there, here it is, hydroxide. Okay? So that has a 1+ charge, a 1 negative charge. One of each of those gives you the balanced formula. Now we said it's in water. The problem didn't actually say that these were aqueous. So you really need to check and make sure they are aqueous. It just says it's taking place in water. I mean, you can put a metal, anything solid, in water, but it's being dissolved is a different thing. When we have sulfates here, sulfates, it says right here in the solubility rules, are always soluble unless they're bonded with calcium, strontium, barium, mercury, lead 2, silver, or ammonium. Well, the hydrogen is none of those, so this is going to be aqueous. And sodium is in group 1, so it says group 1 salts are always soluble. There's no exception for that, so that's aqueous. And now we're ready to find what goes on the right-hand side. I have two two-part compounds. I've got a polyatomic ion here, so that makes that a part by itself. Anytime you have a compound that has more than 2 elements, you want to look and see if you have a polyatomic ion. Polyatomic ions tend to stay together, so we treat those, at least in this class, as if they do stay together. So this is the A part of the formula, that's the B part of the formula. This is the C part and the D part. And so A is going to join up with D. This subscript 2 here doesn't travel because it's not part of a polyatomic ion. So we're simply going to put an H with an OH. At this point in time, you guys should know that's water. And the front part of this, C, is going to go with B. And the front part is positive. It's going to stay in the front. The negative part goes second. So we have Na and SO4. In an acid-base reaction, and this is an acid because it has hydrogen in the front, it's a base because it has hydroxide in the back. In an acid-base reaction, the water that's formed is going to be liquid. In a combustion reaction, we always call it a gas. All right, so sodium compounds, we said, are always soluble. There's no exception. That's going to be aqueous. We need to balance this formula. Sodium, we said, had a 1+ charge. And sulfate over here, we said, has a 2- charge. So we're going to need 2 sodiums to balance out the 2- charge on the sulfate. So this formula is Na subscript 2 SO4. We have a skeletal equation now. We're ready to balance the equation. We need to list all of the elements we have. H, O, S, Na. Not sure why I put oxygen second, but that doesn't really matter. I'm going to count up all the elements or atoms we have of each of these elements. I've got 2 hydrogens here and 1 here. So I'm going to start with 3 hydrogens. I've got 4 oxygens on the left, or in the left formula here. In the second formula, I've got 1. So that's currently 5 oxygens. I have 1 sulfur and 1 sodium. And on the right-hand side, I've got 2 hydrogens here. I've got 1 oxygen right here, plus the 4 here. So I have 5 oxygens. I've got 1 sulfur and 2 sodiums. When you're balancing equations, you always want to balance oxygen last and hydrogen next to last. So all the elements that are unbalanced right now, I only leave sodium. So we're going to put a coefficient 2 in front of the species here that contains the sodium. And that's going to change the number of sodiums, the number of oxygens, and the number of hydrogens. So now we have 2 sodiums. We have 4 oxygens here, and 2 times 1 makes 2 there, so that's 4 plus 2, or 6 oxygens. And I now have 2 hydrogens here. 2 times 1 is 2 here, so 2 plus 2 gives me 4 hydrogens. Okay, so sodium and sulfur now are balanced. We want to save oxygen for last. We want to go to hydrogen. Hydrogen on the left, I have 4. On the right, I have 2. To get a total of 4 hydrogens, I can put a coefficient 2 in front of this species here that contains 2 hydrogens. That's going to give me 4 hydrogens, but it's going to change the number of oxygens as well. We now have 4 hydrogens, and I've got 2 times 1, or 2 oxygens, plus 4 over here, giving me 6 oxygens. And that balances the equation. So now we have a balanced equation. With a balanced equation, we have what we need to balance. We have what we need to do a stoichiometry problem, because stoichiometry requires that we have a balanced chemical equation. Now let's look at the problem again. It says that we have 3.25 grams of sulfuric acid and more than enough sodium hydroxide, and ask how many grams of water are produced. So we're going from one chemical formula, the formula for sulfuric acid, to another chemical formula, the formula for water. One chemical to another. To go from one chemical to another, you have to have stoichiometry, and you have to have a molar ratio. The molar ratio is the heart, if you will, of all stoichiometry. All right, so the first thing we want to do is, because the only way to go from this chemical here to this chemical, that's what the problem's asking you to do, is to have the 2 chemicals in moles, units of moles. So since I know the amount of this, it's 3.25 grams of this, I've got to convert it to moles. Once I convert this to moles, then I can convert from this species in moles to this species in moles, and finally I can produce, I can figure out how many grams there are if I know how many moles of water there are. So we're going to do a dimensional analysis problem. We're going to set it up in dimensional analysis. It's stoichiometry, which is converting from one chemical species to another. You have to have a balanced chemical equation for that. But the method for setting up the problem, the math, is a dimensional analysis setup. So 3.25 grams of sulfuric acid. And we always put those over 1. Now, later in chemistry and later classes in chemistry, if you go on and do chemistry in college and so forth, you'll find there'll be some problems that you don't automatically put your starting amounts over 1. But almost everything we do in this class, if we're doing a stoichiometry problem, you're going to put your starting amount over 1. Now, I said a while ago we've got to convert this into moles. The way you do that is to calculate the molar mass. And so the molar mass is the sum of all the atomic masses of all the atoms in the formula. Okay? And then you write that as an equality statement when you get to the end. So let's add all those up then. Here's our hydrogen, which is, and you just look on the periodic table for these, 1.00794. In this formula there are 2 hydrogens. Then sulfur. And in sulfur there are it's 32.065. That's its atomic mass. So the number we're looking at here on this periodic table is listed on the bottom of each of these boxes. The number at the bottom is the average atomic mass. Okay, you don't use this superscript. You see this superscript 8 here after the 5. That 8 is not actually part of the atomic mass. That 8 just refers you up here to this, where it's telling you that sulfur in nature actually has a range of average atomic masses, ranging from 32.059 to 32.076. The average for the universe, as far as we can tell, is this number, and that's the one we are going to use for our problems, 32.065. We have 1 in the formula, and then we got oxygen, which is 15.9994, and there are 4 of those. And we simply multiply 1 times this, 1.00794 times 2. That gives us 2.01588. And this is just the same as it is because it's times 1, 32.065. And then 15.9994 times 4 is 63.9976. We're adding all these together. In order to keep up with the significant digits, however, we need to know there's an empty slot here and a column here with 2 empty slots. When we add those together, we get 98.07848. Because this 4 and 8 on the end are the result of digits that we don't even know about. We don't know what they would be. They're empty slots. We're going to underline those and round them off. And so the answer we want is 98.078 grams of sulfuric acid. And for this class, you are always required to write it with the units and the species. And when you're calculating the molar mass, you're always required to say that's equal to, you must write this down, equal to a mole of that. Because that's the basic idea behind molar mass. This mass for this chemical species is equal to 1 mole of that chemical species. But it also allows us to build conversion units. And conversion units are built from 2 things that are equal. And we've got 2 things that are equal here. What I want to do is to arrange this conversion unit so the units and species that I put down here have the same units, match the units and species of what's on the top here. And that would be this side of the equality statement. So we're going to put 98.078 grams of sulfuric acid on the bottom. We're going to put the 1 mole on the top, 1 mole of sulfuric acid. Cancel out units, cancel out species, and we're left with moles of that chemical we started with. Now we have what we need to be able to use the balanced equation. The balanced equation, we can assume these coefficients here, this implied 1 on the sulfuric acid and the 2 on the water, we can assume those to be either particles, like 1 formula unit of sulfuric acid and 1 molecule of water, or we can assume those to be moles. Okay, as long as we multiply everything in here by Avogadro's number, we've got coefficients of moles, which makes this math a whole lot easier. So if I assume those to be moles, then I can put 1 mole for this coefficient here, 1 mole of sulfuric acid, and 2 moles of water. Cancel out what we can cancel out. And now we have moles of water. Well, the problem doesn't ask for moles of water. It asks us for the mass of water. So to go from moles of water to mass, we just kind of undo the same thing we did here. We basically build the same thing, but it's built in the opposite direction, more or less. We've got to have the molar mass for water. And so we've got hydrogen, 1.00794. We've got 2 of them in the formula for 2.01588. And we've got oxygen. We've got 515.9994 for the atomic mass times 1 because there's only 1 oxygen in the formula. So 15.9994. We've got 1 empty slot over here. Add them together. That empty slot right there means this 8 is insignificant. We're going to underline it and draw an arrow. And we have 18.015. This 8 makes this 2 round up to a 3. So 0.153 grams of water is equal to 1 mole of water. Again, we're going to be building this conversion unit so that the units from the bottom here match the units and species on the top here. And that would be this side of this equality statement. 1 mole of water. And on the top it's 18.0153 grams of water. Okay? Now you might notice that I've written water 2 different ways. This is the same thing. HOH is still H2O. So moles can cancel and the HOH can be canceled by the H2O. We're ready to do the math now. So listen carefully. In your calculator, the way you're going to do this, to make it go the fastest possible way that you can, there's a lot of ways to put this in the calculator and get the right answer. There's also a lot of ways to get the wrong answer. But the fast way to put these in, and since we're doing a lot of these in this unit, this is all about stoichiometry in this unit, this is the fast way to do it. Multiply everything across the top, put it in your calculator, hit enter. Then divide by this number and hit enter. Then divide by any other numbers on the bottom and hit enter. We only have 1 number to divide by here because dividing by 1 just gives us the same number. But make sure you multiply what's across the top, hit enter, then divide what's in the bottom, enter, again anything else in the bottom, enter, and so forth. Okay? All right. If you haven't been using your standalone calculator to practice, you need to be doing that. Don't use your phone for these. Use your standalone calculator because on the test, you can't use your phone. You have to use a standalone calculator. The more you practice with it now, the more likely you are to be successful when you do this on the test. Okay? So use your standalone calculator for these calculations. Well, I did this and I got 1.193942067 grams of water. For multiplication and division, it's the process or the determining significant digits for multiplication and division is different than it is for addition. With addition, you look to the right and find any empty slots around off those numbers that result, or digits that result. With multiplication and division, you look at the measured or calculated numbers and determine which of those measured or calculated numbers has the least digits. So all of these numbers in this problem, this math here, this is a measured or calculated number here. This is a measured or calculated number here. And this is a measured or calculated number here. All these other numbers are counting numbers. You can see they're all whole numbers. And that's not an absolute test. Some whole numbers are going to be those that you have to use for figuring out significant digits. But most of the time, if it's a whole number, it's a counting number. Okay, it can kind of help you figure it out. But all these numbers here, this has the least digits. There's 3 digits here, 5 here, 6 here. So we want our final answer to have the same number of digits as this number because it's the measured or calculated number with the least digits. And that's the rule for significant digits when you're doing multiplication and division. So we want 1, 2, 3 significant digits, underline everything else, draw an arrow. An arrow is the only allowed operator that shows that you're rounding off. Any other operator we counted as being incorrect. And so this rounds off to 1.19 grams of water. And we're done with that problem. Okay, so the problem we just did, you could call mass-to-mass stoichiometry. Okay, so it's stoichiometry, but there's lots of different types of stoichiometry. Stoichiometry is a large category of the math and chemistry that requires a balanced chemical equation. And it requires a balanced chemical equation because you're going from one chemical species to another. And to go from one chemical species to another, you have to have a molar ratio. And that's all those things are part of stoichiometry. Well, we're going to go now from just doing a single mass-to-mass problem to doing more complex stoichiometry problems. This is where we're going to figure out what's called the limiting reactant. Okay, we're going to find in this problem the limiting reactant. Now, you start off the problem in the same way. You still have to figure out what the balanced equation is. So, if we're going from one chemical species to another, and if you read this problem, that's exactly what's happening, you have to figure out the balanced equation to get the molar ratio in order to convert from one chemical species to another. But to find a limiting reactant, we have to do two different stoichiometry problems. Okay? Now, there's a lot of ways to do that. In most textbooks, they teach you one way to do it, but most of the chemistry teachers I know do it where we keep doing these mass-to-mass problems. So, I'm not teaching you to do two different kinds of stoichiometry problems this early in the game. So, to solve this problem, we're going to have to do two different mass-to-mass stoichiometry problems. Okay? Now, the first thing you got to do is find the balanced equation, figure out the balanced equation. And guys, that was our whole last unit. So I'm just going to pause the video and pause the instruction here. And you guys, as a group, working together in small groups, you can pick a partner to work with. You're going to figure out what the balanced equation is first, and then we'll go from there. All right, so our entire previous unit was about predicting the products of and balancing equations and all that sort of thing. And before that, the unit was on one of the units before that was about balancing formulas. So this is the balanced equation, okay? And now we're ready to start the stoichiometry part of the problem, or the dimensional analysis part of the problem. Now here's the way that we find a limiting reactant. You have to do some kind of stoichiometry that will let you figure out which one of the two reactants, and we have two of them. We have aluminum, we have nickel sulfate. Which one of those two is the limiting reactant? So what's a limiting reactant? A limiting reactant is the chemical that runs out first in a reaction. The limiting reactant is the chemical that runs out first in the chemical reaction. I'll say, okay, since it's the one that runs out first, it's the only one that gets used up. You don't have to write that down necessarily, but since it's the one that runs out first, it's the one that gets used up. And when it's used up, since you have to have both reactants for a reaction to occur, the reaction stops. The limiting reactant limits the reaction because once it runs out, nothing else can happen. Okay? That's why it's called the limiting reactant. Well, for this problem it's done. But there are some other things we have to do after this, after we learn how to figure out what the limiting reactant is. So with the limiting reactant, we're going to figure out which one of these is going to run out first. And the way we're going to do that is to do two separate mass-to-mass problems. Okay? So in this problem, it says we have 3 grams of both aluminum and nickel sulfate. So the weight we're starting with of the aluminum and the weight we're starting with of the nickel sulfate are exactly the same. Okay? So we need to start with one of those and do a mass-to-mass problem to the product. And the product we're looking to make is nickel, the nickel metal. Okay? So what we're going to do is we're going to set up and do just one of these two mass-to-mass problems. Okay? Now you did one as homework, but I'm going to go through this with you, and we're going to do one of these two mass-to-mass problems. Okay? So step 1 then is to find out how much nickel we produced if we start with, what do you want to start with, nickel, or you want to start with nickel sulfate? No, start with nickel, huh? All right, well, we'll start. I got one person for nickel sulfate, one person for Aluminum, which one we go?
Alright.
Huh?
I just want to pass.
Alright, we're going to start with nickel sulfate because that seems to be what everybody's asking for. So step one is to start with one of the two chemicals, and there's 3 grams of both, and we're going to start with nickel sulfate. Okay? And we have to find out how much nickel is going to be produced. So in our balanced equation, we're going to go from nickel sulfate to the nickel here. Okay? In our balanced equation, we're going from the nickel sulfate to the nickel. So we're going to put our starting amount over 1, and we got to get this into moles because we can't go from one chemical species to another without it. So how do we get from grams of nickel sulfate to moles? Find the molar mass, it's called. Yeah, the weight is really what you're saying is the molar mass. So we're going to take nickel, which we're going to look on the periodic table and find its atomic mass, and we'll see that it's 58.6934. I hope you're doing this for yourself and looking on the periodic table so that you can get your mind sort of trained to do this and not just writing it down because, oh, Mr. Tedder wrote it down. You need to know how to do this for yourself because in the test, Mr. Tedder's not going to write it down for you. Okay? And then what's the atomic mass for sulfur?
I got you.
Well, everybody should be looking it up, not just one person.
32.065.
That's actually, that jumping in there is a good thing because that jumping in there means that people are actually looking it up.
Do it, but you know.
It's 0.065.
Oh, 5. Thank you. So that should be a 5 instead of a 9 there. Now, with oxygen, we've got 4 of those oxygens, okay? It is a 5. I'm changing it to a 5 here. Okay? So with oxygen, the atomic mass is 15.9994, but we've got 4 of them. So you've got to multiply that by 4. Or you can add it together 4 times. Well, which one's easier? Yeah. So that's what I want you to do, multiply. And you should be using your standalone calculator. Guys, here's the thing. If you don't practice with your standalone calculator now, when you get to the test, you're likely to make more mistakes. So don't use your cell phone calculator. Get out your standalone calculator, and every time you do these problems in class or at home, practice with your standalone calculator. You get used to it. You know how it works. You don't have to use as much brain power to figure it out when you're doing the test, and you can save that brain power, focus that brain power on the stuff that really is hard. Okay? So what is this times 4, guys? 63.9976. Now, if you've lined up all your digits carefully, you'll notice there's an empty slot right there. That's important. Now, when you add these together, and you got to be smarter than your calculator, folks, because when you put in your calculator, you get 154.997. Right? Did you try that? 154. Is that what you got? 997. But look, what actually belongs in this column right here?
Nothing. 0.
Well, it's not a nothing. A 0 is actually something. Okay? I understand that every time you've taken a math class up to now, 0 is nothing. But 0 is not nothing. 0 is something. Okay, yes?
How do you know what to round to?
Well, if you're doing addition and subtraction, anytime you've got an empty slot to the right, that digit rounds off. Now, what we end up with in the long run is 154.997. But you need to know how to handle those significant digits because sometimes it may not work out so nicely as that. So that's grams.
That's not right.
Oh, you didn't get it right there, Plainway?
.756.
All right, so math error here. It should be 154.756 with a 0 at the end. And that rounds off to 154.756, and you got to say, you have to write it down. It has to be on your paper, you lose points. Grams of, in this case, nickel sulfate. And you've got to say, you've got to write on your paper, it's got to be written down, that equals to 1 mole of nickel sulfate, okay? You have to have it.
1 mole.
All right, so now we're going to build a conversion unit from this, and we're going to put the side of this equality statement that matches these units and this species on the bottom here, and that's this side of the equality statement. So 154.756 grams of nickel sulfate. On the top we put the 1 mole of nickel sulfate. Okay? Now we can cancel out and simplify. Grams are going to cancel, and nickel sulfate is going to cancel, and we have moles. Well, now we can use the balanced equation to go from moles of nickel sulfate to moles of nickel. So what's the molar ratio? 3 and 3. Okay? So we have 3 moles of nickel sulfate in the equation. We also have 3 moles of nickel in the equation. Now we can simplify that. And now we need to go and find the molar mass for nickel to get back to mass. Okay? Well, I've already got that written down here, but let's just write it out the way it's supposed to be. Here's nickel. It's 58.6934. Listen, there's only one nickel. Okay? Only one nickel here. Only one nickel. And so that is the molar mass for nickel. Okay? And so I can put the moles on the bottom, 1 mole. And I can put the mass on the top. So if I just have an element, a single atom element, not a diatomic element, but a single atom element, the atomic mass is its molar mass. You just change it from atomic mass units into grams. Okay? And so now we can simplify this. Moles cancel, nickel cancels. And we're ready to do the math. Now to do the math, to do this math up here in the stoichiometry problem, we're going to multiply what's across the top. 3 times 58.6934. We're going to hit enter. We're going to divide by this number, hit enter again, then hit divide by this number, hit enter again. So let me show you what that looks like on my computerized calculator here. So it's 3.00 times 3 times 58.6934, and I'm going to hit enter. Now I'm going to divide by the 154.756 and hit enter. Then I'm going to divide by the other 3 on the bottom, and that's the number that I get. Okay? So this is the unrounded answer I get. And the units I have left are grams. After I cancel everything else, the species I have left is nickel. I need to round it off to match the least digits in the problem. All right, now we're going to look at the problem and figure out how many significant digits we need in our final answer. So finding significant digits in multiplication and division, guys, is different than it is from addition. Okay? For multiplication and division, we want to find the least digits among the measured or calculated numbers. Okay? So this number here is a measured number. This is a calculated number. Somebody calculated this thing to find this number. Okay, we did, right down here. Okay? Here's a calculated number. We calculated this number. It's right here. Okay? Now, these digits here, these 3s and these 1s, those are counting numbers. Okay? They're not calculated or measured numbers. We don't use those. We only use these 3 numbers to figure out significant digits. And of these 3, this number here has the least digits. 1 digit, 2, and 3 digits. So we want our final answer to also have 3 digits. And so we underline everything else, that all the others are insignificant, and round it off to the 3 digits. Well, that 7 makes the 3 round up to a 4, and we get 1.14 grams of nickel. So that's just the first half. Okay? This is the first half of the problem. Now, you have to calculate from one of the 2 chemical species to the mass of a product. Now you have to go from the other chemical species, the other reactant. What's the other reactant in the problem? Aluminum was the other reactant in the problem. Okay? Aluminum was the other reactant in the problem. So you're going to find you're going to do the same thing with the aluminum, okay, over here, and calculate mass to mass of that same product. So do that again. I'm going to let you guys do that. I'm going to pause the video and let you guys solve for that. Well, hang on. We're kind of running short on time. Let me solve the rest of this for you because you've got to be able to do this, do the homework problem. All right, so we've got to find the mass of nickel if we start with aluminum. Got to find the mass of nickel if we start with aluminum. Look, we've already found the mass of nickel if we start with nickel sulfate. That's one of the two reactants. Now we've got to find the mass of nickel if we start with aluminum. We've got to start with the other reactant. So we started already. We did a mass-to-mass problem starting with this and going to this. Now we're going to do a mass-to-mass problem starting with this and going to this. Both of these are the reactants. We're using this process to find which one is the limiting reactant. Okay? So we have 3 grams. The problem says we have 3 grams of both the aluminum and the nickel sulfate. So we're going to start with 3 grams of aluminum. The atomic mass of aluminum is 26.9815. Very good, guys. Aluminum, and that's equal to 1 mole of aluminum.
So you put 1 mole over 26.981538. That's a what? You don't have to round it.
No, you don't, because there's nothing to round here. So you're right. All right, so we're going to cancel out. I haven't put grams of aluminum on the bottom here yet. Those cancel out. All right, now we need to go to the balanced equation. Let me move this fraction down just a little bit to make it work out easy, look better for us. Okay, so now we want to go to the molar ratio. Once we've got aluminum into moles, then we can go to the molar ratio. The molar ratio is going to be the moles of aluminum to the moles of nickel. Well, there's 2 moles of aluminum and 3 moles of nickel. Since I have moles of aluminum here, I want moles of aluminum on the bottom, and we said there were 3 moles of that. 2 moles of that, rather. 2 moles of aluminum. Okay? And there's 3 moles of nickel. Now we can simplify this and cancel out moles of aluminum. And so we're ready now to convert the the nickel moles back into mass. Okay? Well, that means we need molar mass for this. But we've already calculated that, haven't we? We already found that the mass of nickel was 58.9834 grams in 1 mole. So we're going to put the 1 mole of nickel on the bottom so I can cancel moles of nickel. And 58.6934 grams of nickel on the top, because we've already calculated that molar mass. We don't have to do it twice. Okay? And we do all the math, and we find that this is going to give us 9.788926.784 grams of nickel. Now your calculator may have a few less digits or a few more digits on the right. How many significant digits do we need? 3. Going to round it off. 9.79 grams of nickel. All right. And what we need to do is compare this amount of nickel that we calculated here to the amount of nickel we had before. Okay? In the previous problem, we found there was 1.14 grams of nickel. But in this problem, we found there's 9.79 grams of nickel. Okay? That smaller number for this mass-to-mass calculation tells me that this species is the limiting reactant. The smaller number of the product, the smaller amount of the product tells me that the species I started with in this calculation is the limiting reactant. Okay? So in this equation here, we had 2 reactants. We had nickel, we had I'm sorry, we had aluminum, we had nickel sulfate. Since calculating this product with this chemical gave me a smaller mass than calculating this product with this chemical, this one must be the limiting reactant. It's the one that runs out first. Okay? And so we're going to reach the conclusion that nickel sulfate is the limiting reactant. Okay? Because I got less mass of product starting with that reactant. Okay? The amount you got of the product was smaller. Alright, here's your homework.